Imagine a star so dense it packs more than the Sun into a city-sized sphere, and then spins 716 times every second, hidden deep inside a crowded cluster near the heart of the Milky Way. Tonight's journey drifts into the world of PSR J1748 2446ad, the fastest known cosmic clock, as its quiet pulses echo through Terzan 5 and across interstellar space. If you enjoy falling asleep to slow, thoughtful voyages like this, please remember to like the video and subscribe for more calming trips among the stars. PSR J1748 2446ad spins 716 times each second inside the globular cluster, Terzan 5 deep toward the crowded bulge of the Milky Way. It matters because a neutron star spinning this fast pushes against the limits of how solid ultra-dense matter can be before it tears itself apart. By the end of this quiet journey, the listener understands how this tiny star, its cluster home, and its magnetic surroundings fit together into one calm, coherent picture. Around it, Terzan 5 appears as a faint, hazy knot in a telescope image, yet within that knot hundreds of thousands of stars drift inside a shared gravitational well. The cluster hangs in the sky like a softly glowing seed thick with aging suns, whose light is partly veiled by dust between the cluster and Earth. In that dim crowd, stellar encounters happen more often than in the quiet suburbs of the galaxy. So close, passes and exchanges between stars steadily reshape who orbits whom. Over long stretches of time, such encounters increase the chances that a once isolated neutron star gains a partner, forming a tight binary whose history is written into the rapid spin seen today. Seen in this way, PSR J1748 2446ad is not only an odd record holder, but also a small, clear signpost of how densely packed environments sculpt the lives of stars long after their birth. The scene can be imagined as a softly turning swarm, where each star traces a slow path through the shared cluster halo, while the neutron star races internally like a hidden gear. Against this gentle background, the pulsar itself is invisible to ordinary sight, yet its presence is betrayed by its heartbeat, like radio flashes that reach radio dishes on Earth. A pulsar is simply a neutron star whose strong magnetic field and fast rotation create narrow beams of radiation that sweep through space, turning the object into a distant spinning beacon. When one of those beams crosses Earth, instruments pick up regular pulses like clock ticks that reveal the spin rate and stability of the star with remarkable precision. For PSR J1748 2446ad, each tick is separated by a little over 1,000th of a second, a rhythm so quick that a human blink would span many hundreds of rotations. This extreme regularity allows astronomers to time the pulses over many months, measuring how the star orbits its companion and how its rotation might change with almost metronomic sensitivity. In the middle of the cluster, the binary system sits inside a bath of starlight gas and dust, so the pulses must weave through this soft fog before they ever leave Terzan 5. On their way outward, they also cross dense inner regions of the Milky Way. Free electrons there, slow low-frequency waves more than high ones, stretching each pulse into a soft descending note. This effect, called dispersion, acts like a natural prism for radio waves, and by measuring it, astronomers infer how much material lies between the pulsar and Earth. The cluster therefore serves as both a cradle and a screen hosting the neutron star, while also shaping the signal that finally arrives at human-built instruments. In that context, the fastest known spinner feels less like an isolated curiosity and more like the sharpest point of a much larger pattern playing out across the cluster. The gentle lesson here is that extreme behavior in the universe often grows naturally out of crowded, long-lived environments, rather than sudden isolated events. Terzan 5 itself may be the fossil remnant of an early building block of the Milky Way, a fragment of ancient star-forming history now compressed into a compact shimmering sphere. If so, PSR J1748 2446ad becomes a messenger from that formative time, carrying in its spin and orbit subtle records of how stars and gas once moved in the young galaxy. Even without knowing every detail, the simple fact that such a rapid pulsar survives inside this dense stellar ball reassures observers that nature can maintain fragile balances for immense spans of time, step by step as the pulses are tracked and the cluster is mapped. The relationship between the star, its environment, and the surrounding sea of plasma grows clearer and more stable in the mind. The view moves from the outer appearance of Terzan 5 as a faint blur to the realization that a city-sized object spins at great speed near its core. It narrows step by step while the tone stays calm. The listener is gently led to see PSR J1748 2446ad, not as a threat or a violent engine, but as a precise, steady rhythm nested inside a peaceful but crowded stellar neighborhood. In later sections, the focus moves inward from this broad cluster portrait toward the neutron star itself, its dense interior and its magnetic surroundings. Each return to this scene carries the same reassuring idea of a cosmic clock that simply keeps turning. Terzan 5 lies toward the galactic bulge as a compact concentration of ancient stars wrapped in dust and faint foreground gas. The cluster behaves like a dense stellar city, where close encounters between stars are common and slowly reshape orbits over immense times. In this kind of environment, the stage is set for neutron stars like PSR J1748 2446ad to find partners and eventually become rapidly spinning pulsars. The cluster itself spans only a few tens of light years, yet it contains hundreds of thousands of stars bound inside one shared gravitational well. Each star circles the cluster center, under that common pull moving in 3 dimensions like fireflies in a dark room. The overall pattern changes very slowly, but local neighborhoods inside the swarm can shift as stars drift past one another. Some stars plunge through the crowded core, others linger in the outskirts, and together they create a gentle but persistent background of gravitational nudges. This quiet stirring means that pairs of stars can be pushed closer together or even broken apart, especially when a heavy remnant passes nearby. A neutron star, the collapsed core of a massive star after a supernova, carries strong gravity in a city-sized sphere. When such a compact object moves through Terzan 5, its pull can act like a subtle hook during a close passage. In a place where so many stars share such a small volume, these chance meetings are more frequent than in the calmer regions around the Sun. Over long stretches of time, an initially solitary neutron star can pick up a companion and begin orbiting in a newly formed pair. In a binary system like this, the 2 objects circle a shared center in a tight repeating dance set by their mutual gravity. Against the broader background of the cluster, such binaries appear as tiny details. They matter because they create the conditions needed to spin up a neutron star. The cluster therefore works like a slow workshop building special orbital arrangements that later feed matter onto neutron stars and change their rotation. Observations of Terzan 5 reveal many millisecond pulses, not just the record holder, showing that this environment routinely produces rapidly rotating remnants. The presence of so many examples in one place turns the cluster into a natural laboratory where different systems display different stages of a shared evolutionary path. Some pulsars orbit very close to their companions, some travel on wider paths, and some show eclipses when material from the companion blocks the pulses. PSR J1748 2446ad belongs to this family positioned somewhere within the crowded cluster core. Its extreme spin marks the outer edge of what such environments can achieve. Around it, the light of ordinary stars still dominates any optical image, so the pulsar remains hidden, known mainly through careful radio and high-energy observations. Dust along the line of sight further dims and reddens the starlight. The cluster appears more subdued than it would in a clearer region of space. For someone picturing the scene, Terzan 5 can appear as a softly glowing sphere of stars with a dense centre. Fainter members form halos that thin into the surrounding galactic field. Inside that sphere, the gravitational potential acts like a smooth bowl, keeping most stars confined even as they move on complex paths. Occasionally, a close approach or three-body interaction shifts a star onto a new orbit. Partners may be exchanged, or a binary may tighten with only a tiny change in energy. These small adjustments, repeated countless times, slowly build up the unusual systems that later stand out in radio surveys as millisecond pulsars. The fact that Terzan 5 hosts the fastest known spinner suggests that the cluster has been particularly effective at creating and preserving such exotic configurations. It hints at a long history rich in massive stars' supernova explosions and the formation of many neutron stars. Those remnants now drift as invisible points among luminous giants and dwarfs. Over its lifetime, the cluster likely loses some members to the wider galaxy through tidal stripping. Even so, its core remains dense enough to keep the encounter rate high today. This continuing activity means Terzan 5 is not a frozen relic, but a slowly evolving system where new interactions and binary transformations still occur. For the story of PSR J1748 2446ad, idea quietly guides the scene. The cluster environment supplies both raw material and gentle stirring required to create a record-breaking millisecond pulsar. Later, the focus can narrow to one neutron star and one companion. The surrounding sea of stars always forms the backdrop that makes such a system possible. Long after individual stars exhaust their fuel, the shared gravity of Terzan 5 keeps them moving together. Within that steady motion, rare objects like the fastest spinner emerge as natural outcomes rather than isolated surprises. In a tight binary system, a neutron star can steal gas from its companion and slowly spin itself up into a millisecond pulsar. This quiet exchange of matter explains how a once ordinary remnant in Terzan 5 can eventually become something as extreme as PSR J1748 2446ad, spinning hundreds of times each second. The path begins with a massive star that lives fast, burns bright, and then collapses in a supernova, leaving a dense neutron star behind. After the explosion fades, that remnant rotates quickly at first and slowly loses speed as it radiates energy away into space. On its own, it would simply cool and spin down, becoming a faint, quiet object in the crowded cluster. The story changes when the remnant drifts through the dense core of Terzan 5 and passes close to another star. In such a packed environment, three bodies can meet, and gravity can reshuffle partners so that the neutron star ends up bound to a new companion. Over time, the pair settles into an orbit circling their shared center, like two stones tied to the same string. At first, little happens beyond this steady revolution, but the companion star continues its own evolution. Its outer layers warm and expand, gradually pushing closer to the region where the neutron star's gravity dominates. When the swollen outer atmosphere reaches a certain distance, gas no longer remains securely attached to the companion. A gentle stream begins to slip away through the inner side of the orbit, drifting toward the neutron star. This slow, continuous transfer of material is what astronomers call accretion, the steady feeding of one body by another. Instead of falling straight onto the neutron star, the gas forms a rotating stream that wraps around it. Conservation of angular momentum guides the flow into a thin, bright disk that spins like a flattened whirlpool. Within this disk, particles rub against each other and against magnetic fields, creating friction that heats the gas to high temperatures. As the gas warms, it slowly loses orbital energy and spirals inward, moving toward the compact star at the center. At the same time, the disk carries rotational energy and passes part of it to the neutron star, much like a spinning flywheel, delivering pushes to the smaller object in its middle. Each small parcel of gas adds only a tiny amount of spin, but the process continues for millions or even billions of years. Over such long stretches of time, those tiny pushes accumulate into a profound change. A star that once rotated only tens of times each second can be wound up to hundreds of turns per second. In the case of PSR J1748 2446ad, this gradual winding likely drives the astonishing rate of 716 rotations each second. During the most active stages, the disk shines strongly in high-energy light. Gas plunging onto the neutron star surface releases gravitational energy as heat and X-rays, turning the system into a luminous X-ray binary. In that phase, the neutron star's magnetic field and spin still shape the flow, but the bright variable X-ray output dominates what distant instruments see. As the companion star loses mass and the available fuel diminishes, the inflow from the disk weakens. There comes a time when the neutron star's rapid rotation and magnetic field can push back against the remaining gas. The strong field channels outflowing particles into a wind that clears the surroundings and prevents new material from piling up close to the surface. When the space around the star becomes clean enough, the radio pulsar mechanism can emerge. Narrow beams from the magnetic poles sweep through space with each rotation, turning the system into a stable millisecond pulsar powered by rotation instead of by fresh accretion. The neutron star is then described as recycled because its rapid spin no longer comes from its birth, but from the long spin-up phase in the binary. For PSR J1748 2446ad, the partner star remains in a day-long orbit, and its outflow still plays a role. Gas driven off the companion by radiation and particle winds can form a cloud that occasionally blocks the radio beam. During these eclipses, the pulsar signal disappears or grows faint for a large part of the orbit, then returns when the line of sight clears again. This behavior quietly confirms that the system is still exchanging energy and matter, even though the main spin-up has already taken place. Seen as a whole, the binary behaves like a self-regulating arrangement. Gravity draws material inward spin, and magnetic fields push material outward, and the two influences balance to hold the neutron star at an extraordinary but remarkably stable rotation rate. A record-breaking spin frequency then appears not as a sudden fragile accident, but as the natural outcome of a very long and gentle negotiation between two stars. For the broader picture, this pathway shows how a dense cluster environment, repeated encounters, and slow mass transfer can turn a single supernova remnant into the fastest known pulsar. From here, the story can move inward to the interior of the neutron star, where this rapid rotation sets strict conditions on how tightly matter must hold together deep below the surface. In a body as compact as PSR J1748 2446ad, mass and radius work together to decide whether the star can survive its extraordinary spin. The central idea is simple. A star this small and heavy must be strong enough in a deep physical sense to hold itself together while turning hundreds of times each second. A typical neutron star packs more than a sun's mass into a sphere only about 20 kilometers wide, and this one likely follows a similar pattern. The surface lies not far above where gravity will become strong enough to trap light, so the pull at that boundary is intense and unwavering. Matter there is squeezed far beyond the density of ordinary atomic nuclei, creating a state that does not appear anywhere else in the universe. In imagination, the neutron star is like a gigantic atomic nucleus scaled up to the size of a city. Gravity, not electric forces, holds its particles confined. Around that dense center, the structure arranges itself in layers that respond to pressure and composition. The outermost region forms a thin solid crust about a kilometer thick, where ions arrange into a lattice floating in a sea of mobile electrons. Deeper down, nuclei grow more exotic and neutron-rich, and some neutrons leak out to form a quantum fluid that threads through the solid structure. At even higher pressures, the distinction between individual nuclei fades. Matter behaves more like a continuous soup of neutrons, with a smaller share of protons and electrons mixed in. Somewhere beneath the crust, neutrons likely slip into a superfluid state, a frictionless form of matter that can flow without resistance through tiny channels. The deeper core may host a superconductor as well, where charged particles move in an ordered way and carry magnetic fields in thin tubes. The detailed recipe for this interior, the relation between pressure and density at each depth, is what physicists call the equation of state. In simple terms, that relation tells how stiff or soft the matter is and how easily it yields when gravity squeezes it. A stiffer interior produces a star with a slightly larger radius for the same mass, while a softer interior allows greater compression and a smaller radius. For a fast-spinning neutron star, this balance matters. If the star is too soft, the outer layers cannot support the centrifugal forces from rapid rotation, and the star would fly apart at the equator. If it is too stiff, it might resist that breakup but produce a radius that conflicts with other measurements and observations. The observed spin of 716 rotations per second sits close to the range where these competing effects meet. It suggests that PSR J1748 2446ad has a radius and internal stiffness within a narrow band of possibilities. Models where matter is much too squishy or unrealistically rigid fall outside that band. In practice, timing the pulses and estimating the stellar mass feed directly into models of how neutrons and protons behave under extreme compression. Even without a perfectly known mass, the combination of such a high frequency and the absence of signs of structural failure already carries weight. It shows that nature can build a neutron star whose material withstands enormous strain without tearing, cracking, or spreading into a disk. This conclusion brings a gentle but far-reaching message. Deep inside the star, pressures soar many times beyond anything achievable in laboratories, yet the structure endures layer above layer, rotation after rotation. Each turn of the star reshapes it into an oblate form wider at the equator than at the poles, yet the overall figure remains stable. The thin, solid crust rides on top of the denser interior like a shell. It carries mountains no higher than a few centimeters in crushing gravity. In such conditions, even small bumps weigh as much as great ranges would on a planet. Under that shell, the superfluid interior quietly redistributes angular momentum, smoothing out tiny irregularities in the rotation over long spans of time. Together, these layers form a single coherent body that behaves like a nearly perfect spinning top despite its violent birth. When this picture connects back to Terzan 5 and to the recycling process in the binary, PSR J1748 2446ad appears as the endpoint of many gentle adjustments. Those adjustments work together in quiet harmony. The dense matter inside sets the rules, the binary feeding sets the spin, and the cluster environment provides the stage. The result is a compact star whose mass, radius, and internal strength allow it to spin faster than any other known neutron star and remain whole. In this way, the record spin does not feel precarious, but quietly supported by deep invisible physical order. The same framework later guides the understanding of its magnetosphere, where those interior properties shape fields and radiation far above the surface. Around PSR J1748 2446ad, the magnetic field creates an invisible structure that shapes almost everything leaving the star. The simple idea is that this field reaches out into the plasma around the neutron star and carves a magnetosphere, a region where charged particles no longer move freely but follow curved magnetic paths. A magnetic field line is just a way to picture that direction, a thread that shows how a small compass would point at each location. Near the surface, the field of a pulsar resembles that of a bar magnet, with lines emerging from one magnetic pole and re-entering at the other. The entire pattern is anchored in the solid crust described earlier, so as the neutron star turns, the magnetic field pattern turns with it. In imagination, the star can be seen as a small, dense sphere at the center, with arcs of invisible wire looping out and back, while the whole arrangement spins hundreds of times each second. Close to the neutron star, many of these field lines remain closed. They leave the surface arch outward and then curve back, forming loops that trap charged particles in smooth, continuous paths. Particles inside these loops move along the lines, bouncing between mirror points, but the overall pattern stays confined within a few stellar radii. This closed zone acts like a protective cage around the star holding plasma that co-rotates almost as a solid body with the crust. Slightly farther out, some field lines do not return. They open into space and stretch outward instead of closing back on the star. These open field lines define escape routes for particles. They channel particles into outflows and carry energy away as winds and radiation. The polar regions where open lines cluster become special places in this architecture. They are the gates through which the magnetosphere connects to larger scales. In a pulsar, the main radio beams arise near these polar caps where open field lines leave the strongly magnetized surface. As the neutron star rotates, the magnetic axis is usually tilted relative to the spin axis. This misalignment means that the polar caps do not sit at the rotational poles, but instead describe circles in space as the star turns. The result is a pair of narrow beams that sweep through space like the cones from a slow-moving lighthouse lamp. The magnetosphere translates the steady spin and constant magnetic field into a rotating pattern of radiation. For PSR J1748 2446ad, this pattern turns at an extraordinary rate, yet the principle is the same. The beams sweep past any distant observer aligned with them, and each sweep produces the pulses that radio telescopes detect. The closed and open regions cooperate to sustain this behavior. Closed lines keep a reservoir of particles tied to the star, while open lines provide pathways for those particles to escape and form a pulsar wind. Currents flow along the field lines and complete circuits through the magnetosphere, helping to maintain electric fields that accelerate new particles near the surface. In broad terms, the magnetosphere behaves like a self-organizing machine that balances rotation, magnetic tension, and particle motion. For the listener, it can help to picture the structure as a softly glowing cage surrounding a spinning ember. Near the surface, the cage is dense with loops. Higher up, some of the wires stretch outward and never return. The whole cage turns steadily, and along the open wire, small sparks travel outward at almost the speed of light. Nothing in this scene is rigid because plasma can shift and adjust, but the overall shape remains stable over many rotations. The extreme spin of PSR J1748 2446ad compresses this architecture in a subtle way. Fast rotation makes it harder for distant points in the magnetosphere to keep up with the star. Co-rotation demands that farther regions move more quickly, and there is a limit beyond which that motion would have to exceed the speed of light. This limit defines the light cylinder a boundary where the simple closed loops of a bar magnet no longer work. Inside that radius, field lines can remain almost locked to the star. Outside, they must open, twist, or reconnect. Even before the light cylinder is discussed directly, the listener can sense how rapid spin tightens the inner magnetosphere. Field lines bend more sharply, and the volume that co-rotates shrinks compared with slower pulsars. The geometry of open and closed zones adjusts accordingly, setting the size of the polar caps and the spread of the radio beams. This structure quietly controls how long each pulse lasts and how bright it appears, because the width of the beam and the path of the line of sight through it both depend on the field layout. From the perspective of Terzan 5, the magnetosphere is a tiny detail around a city-sized star. From the perspective of radiation and winds, it is the entire stage. It mediates between the dense interior described earlier and the empty cluster environment beyond, turning deep gravity and rapid rotation into steady observable signals. Later, as attention moves further outward toward the light cylinder, and the regions where co-rotation finally fails, this same architecture continues to guide the flow of particles and energy, keeping the story smooth and continuous from the stellar surface to the edges of the pulsar's influence. In the magnetosphere of PSR J1748 2446ad, the polar caps act as compact engines that connect the star to surrounding space. A polar cap is the small area around a magnetic pole where open magnetic field lines leave the surface and extend outward instead of looping back. Put simply, it is the footprint of the open field region on the crust. Because the star spins so quickly, rotation and magnetic field combine to create strong electric fields near these caps. Those electric fields have a component along the magnetic lines, and that component pulls charged particles away from the surface. Electrons and positrons are dragged from the crust or from a thin atmosphere and are pushed outward along the curved lines. In imagination, each polar cap becomes a tiny launch pad, where invisible rails rise from the surface and carry particles upward. The surface below this activity is likely hotter than average, warmed by the steady rain of energetic particles that fall back after looping through the magnetosphere. Above the hot patch lies a region where the mix of charges may not perfectly match what is needed to cancel the electric field. That imbalance forms an acceleration gap, a narrow zone where particles feel a net push along the field lines. In that gap, even a modest voltage can give enormous energies, because the field acts over very short distances in extreme gravity. Newly freed particles in the gap quickly reach speeds close to light speed. As they race along the curved magnetic lines, they emit high-energy photons. This emission, known as curvature radiation, appears whenever a fast-charged particle is forced to follow a bent path. Some of the photons escape into space and join the general radiation from the pulsar. Others travel into regions where the magnetic field is strong enough to alter their fate. Under suitable conditions, a single energetic photon in such a field can turn into an electron and a positron. This step pair creation converts light into matter and begins a chain reaction. The original particles from the gap therefore seed a growing cloud of new charges. Each new particle also radiates as it moves, creating more photons that can in turn make more pairs. After a short time, the region above the polar cap fills with the thin plasma of electrons and positrons. This plasma is very light compared with air, yet it is dense enough to carry electric currents. These currents follow the magnetic lines and close circuits through the wider magnetosphere. As the plasma density grows, it begins to screen the accelerating electric field that first created it. The gap shrinks until a balance forms between particle supply and the remaining electric field. In this way, the polar cap region behaves as a self-regulating engine. Whenever charge density drops, the field grows stronger and accelerates more particles. When density rises, the field weakens and the flow settles back. For PSR J1748 2446ad, the extreme spin means this cycle repeats more than 700 times each second. Each rotation sweeps the open field lines and their attached plasma around the star. The same small patches of crust see this process over and over for millions of years. Over long spans of time, returning particles can etch subtle hotspots into the thermal pattern on the surface. Those warm regions cool by emitting soft X-rays, adding a faint glow that reveals the footprints of the polar caps. Farther from the surface, the plasma rising from the caps helps define the region where radio emission is produced. Radio waves likely form at heights, where the density and motion of particles allow them to radiate in step and reinforce one another. This kind of coherent emission turns many small charges into one strong narrow beam. While the exact microphysics remains uncertain, the large-scale role of the polar caps is clear. They are the gates through which particles leave the neutron star and join the magnetosphere. Through these gates, rotation loses energy in a controlled way, gradually slowing the star as the ages pass. From a calm distance, each polar cap can be pictured as a tiny bright door on the surface. That door opens into a long invisible corridor of field lines. Streams of charges flow through those doors and along those corridors, guided by the spinning magnetic structure described earlier. The regular radio pulses detected on Earth are the softened, distant consequence of this local activity above the caps. Slight shifts in the acceleration process or the pair cascades can alter pulse shapes, intensities, or polarization patterns. In a record spinner like PSR J1748 2446ad, the rapid repetition of the polar cap cycle builds an especially stable rhythm. The star turns the cap's launch particles, the magnetosphere reacts, and the beams quietly sweep across the cluster and the wider galaxy. Seen against the still background of Terzan 5, these tiny regions near the magnetic poles act like small but powerful engines. They link the dense interior of the neutron star to its outer environment and to detectors listening from far away. In the regions above the polar caps of PSR J1748 2446ad, the creation of particle pairs turns a sparse environment into a gently glowing sea of charges. Once a few particles are accelerated to high energies, they do not travel alone for long. Each one leaves a trail of radiation that can split into new particles, and those new particles continue the process. Near the surface, freshly lifted electrons and positrons race along strongly curved magnetic field lines. Their paths bend because the lines themselves curve around the neutron star and close back or open outward. A charged particle forced to follow such a path emits high-energy photons, which stream ahead of it along the field. In the intense field close to the star, some of these photons gain the right combination of energy and angle to transform into matter. A single photon then becomes an electron and a positron, a pair that suddenly appears where there was only light. These newborn particles inherit much of the original energy and also move along the magnetic field. As they do, they emit more radiation. That radiation can again produce pairs. In a short distance, one original particle can give rise to a whole family of descendants. The process is called a pair cascade because the number of particles multiplies in a branching sequence. At first, the cascade grows within narrow funnels above the polar caps. The base of each funnel lies in the acceleration gap where electric fields push the first charges to high speed. As the stream rises, more and more particles join. Together they form a thin plasma, a mixture of electrons and positrons that behaves like a fluid and responds collectively to electric and magnetic fields. The density of this plasma does not become very large compared with ordinary matter, but it is enough to carry currents and shape fields. Soon the local charge density grows high enough to partially screen the electric field that started the cascade. When that happens, acceleration weakens. The flow settles into a steady state where just enough particles are created to maintain the currents needed by the global magnetosphere. In this balanced regime, the pair cascades no longer explode outward, but instead hum along quietly, renewing the plasma as it drifts away along open lines. Around PSR J1748 2446ad, these processes repeat over 700 times each second. Every rotation passes the same field lines through the acceleration region again, and each pass rebuilds the streaming plasma if it has thinned. Over long periods, the funnels of pairs become persistent features of the magnetosphere. They extend along the open field lines all the way toward the boundary where co-rotation fails and the light cylinder begins. Within these streams, particles move almost at the speed of light, but their collective pattern turns smoothly with the star. From a distance, the entire structure can be pictured as softly luminous curtains wrapped around the open field regions. Near the surface, the curtains are narrow and bright. Farther out, they spread and thin. Between these streams and the closed field regions lie boundary layers where conditions change. Their field lines shift from returning loops to open paths, and charges from cascades can leak into nearby zones. Some particles are trapped temporarily and then released while others escape promptly into the pulsar wind that flows beyond the light cylinder. The presence of pair plasma modifies how electromagnetic waves travel through the magnetosphere. Radio emission generated at particular heights interacts with this medium. Waves can be refracted, split into modes, or polarized in different ways as they pass through the charged fog. Subtle changes in the density or shape of the streams can therefore alter the observed pulse shape and polarization seen at Earth. For PSR J1748 2446ad, the rapid spin keeps these structures under constant centrifugal stretching. Even so, the overall pattern remains remarkably stable on human timescales. That stability allows astronomers to treat the pulsar as a clock, while still recognizing that a living plasma fills its surroundings. At the same time, small irregularities in the pair production process may create low-level noise in the timing. Tiny wanderings in pulse arrival times that hint at shifting currents or changing gap conditions. Against the wide, calm background of Terzan 5, this constant renewal of charges might seem like restless activity. Yet in the frame of the pulsar it is a stable routine repeating predictably as the star turns. Deep inside, dense matter holds its shape. At the surface, magnetic fields anchor the polar caps. Above them, pair cascades quietly feed the magnetosphere with the plasma it needs. All three layers, interior surface and surrounding plasma, work together to let PSR J1748 2446ad sustain its record spin while still sending clear signals across the galaxy. In the next step outward, this sea of charges meets the limit where field lines can no longer keep up with the spin, and the light cylinder marks a gentle boundary between ordered co-rotation and freer motion into space. In the magnetosphere of PSR J1748 2446ad, there is a quiet but important boundary, where ordered rotation begins to give way to freer motion. That boundary is the light cylinder, an imaginary surface where a point forced to co-rotate with the star would need to move at the speed of light to keep up. Inside this radius, magnetic field lines and the plasma attached to them can still track the spin almost rigidly. Beyond it, they must open, twist or break because nothing can be carried around faster than light. The idea is simple even though the details are complex. The faster a pulsar spins, the closer this boundary moves toward its surface. For PSR J1748 2446ad, which turns hundreds of times each second, the light cylinder lies only a modest distance from the neutron star compared with slower pulsars. That means the entire co-rotating magnetosphere fits into a relatively tight volume around the star. Near the surface, as earlier sections have shown, field lines loop out and back in graceful curves, and others reach outward along polar funnels. Plasma from pair cascades flows along them, joining currents that shape the field. As these open lines stretch away, rotation drags their footpoints around, and the lines themselves begin to wind into gentle spirals. The closer a field line approaches the light cylinder, the harder it becomes for the plasma on that line to trace the star's motion without breaking the universal speed limit. Inside the light cylinder, charges still move at nearly the speed of light along the lines, but the pattern of the lines can stay tied to the star. At the light cylinder, the pattern can no longer remain fully locked in place. Beyond it, much of the magnetic structure opens and becomes part of an outflowing pulsar wind, a stream of particles and electromagnetic waves that carries energy away. In imagination, the light cylinder can be pictured as a cylindrical shell wrapped around the spinning star aligned with its rotation axis. The radius of this shell is the distance where a point on the shell, if it rotated with the star, would rush around at light speed. For this record spinner, that shell sits relatively close in, so the transition between co-rotating plasma and outward flowing wind occurs not far above the region where the radio beam is formed. The small size of the co-rotating zone means that the currents and fields inside it must adjust quickly as the star turns. Each rotation threads new plasma from the polar caps into the open field region and pushes older plasma outward toward the boundary. Some of the field lines that cross the light cylinder may reconnect, changing their shape and releasing energy in the process. This reconnection can help peel magnetic flux away from the star, allowing the overall structure to maintain a steady state despite the rapid spin. In the steady view, the light cylinder marks the outer edge of the dynamical influence of the star's rotation. Inside it, rotation and magnetic tension guide particles in nearly circular patterns around the axis. Outside, inertia dominates, and particles stream away, pulled by the combined influence of fields and their own momentum. The pulsar wind that emerges beyond the light cylinder carries most of the rotational energy loss. Over time, this wind slows the star in a very gradual way. Each second, a small amount of rotational energy leaves the neutron star and spreads through the surroundings as fields and particles. Because PSR J1748 2446ad spins so rapidly, even a tiny change in its spin corresponds to a significant energy release, yet on human timescales the change is almost unnoticeable. The light cylinder therefore acts as the gateway through which the star's rotation feeds the wider environment. Within Terzan 5, that flow may contribute to heating thin gas, or shaping subtle structures in the intracluster medium, though most of the energy simply disperses into the broader galactic environment. From the point of view of observations, the region near the light cylinder also helps define the exact shape and timing of the radio pulses. Small variations in the plasma density or field geometry around this boundary can slightly alter the path and phase of the waves that escape. For a pulsar used as a clock, even tiny shifts matter, because they influence the precise arrival times measured at Earth. In PSR J1748 2446ad, the compactness of the light cylinder and the steady feeding from pair cascades together support the remarkable regularity of its pulses. The star spins, the magnetosphere turns with it up to the light cylinder, and beyond that surface the wind carries away the excess motion. This quiet balance between rotation fields and outflow allows the fastest known spinner to keep acting as a stable beacon, even while it constantly trades a small portion of its spin for streams of energy crossing the edge of its light cylinder and flowing outward into space. The way PSR J1748 2446ad shines towards space depends strongly on the shape of its radio beam and how that beam sweeps across the sky. At the simplest level, the beam forms where coherent radio emission arises high above the polar caps, following the open magnetic field lines that leave the surface and stretch outward. Those lines define a cone or a fan of radiation, not a uniform glow in all directions. As the neutron star spins, the tilted magnetic axis causes this cone to slowly trace a circle around the rotation axis, just as a lighthouse lamp turns and sends its narrow beam around the horizon. If a distant observer lies within the path of this sweeping cone, a pulse appears every time the beam crosses the line of sight. If the observer sits outside the path, there is no radio pulsar at all, only a silent neutron star. The geometry therefore decides who sees the pulses and who does not. In a cluster like Terzan 5, which likely hosts many neutron stars, only a fraction ever reveal themselves as pulsars because of this geometric selection. The beam itself is not infinitely thin. It has a finite width that depends on the height of the emission region and on the spread of the open field lines. Higher emission usually corresponds to a broader cone because lines diverge as they rise. In very fast pulsars like PSR J1748 2446ad, the open field region is compressed, and emission may occur relatively close to the star compared with slower pulsars. That configuration can influence both the width of the beam and the detailed shape of each pulse. When astronomers describe beam geometry, they often think in terms of angles. One angle gives the tilt between the magnetic axis and the rotation axis. Another angle measures how far the line of sight sits from the rotation axis. Together, these angles define a path across the beam each time the star turns. If the line of sight passes near the center of the beam, the pulse appears broad and symmetrical. If it skims the edge, the pulse becomes narrower and sometimes more complex, with sharp leading or trailing components. The fraction of each rotation during which the pulsar appears bright is called the duty cycle. In a record spinner with a period of about 1.4 milliseconds, the pulses themselves occupy only a small slice of that time. For PSR J1748 2446ad, the duty cycle is expected to be a few percent or less, meaning that the beam shines toward the observer for only a tiny fraction of each spin. In the time between pulses, the beam points elsewhere, and the signal drops back into quiet background noise. Despite this brief duty cycle, folding many pulses together in analysis builds a stable average profile. That profile captures the characteristic shape of the beam along the path cut by the line of sight. Small features in the profile reflect finer structure in the emission zone, such as nested cones core components or patches of enhanced brightness. In millisecond pulsars, profiles often show sharp, well-defined peaks, consistent with emission, arising from compact regions in a tight magnetosphere. For PSR J1748 2446ad, any detailed profile carries the imprint of its rapid spin, the size of its open zone, and the exact viewing geometry. In imagination, the star can be pictured as a tiny spinning top at the center of a gentle cone of radio light. The cone sweeps through space like a slow hand on a clock, even though the actual rotation is extremely fast. An observer near the axis of the cone would see a pair of broad pulses each turn, while one near the edge might see only a thin flash or none at all. This simple picture helps explain why so many neutron stars in Terzan 5 remain undetected as pulsars, even if their magnetospheres work in similar ways. Their beams simply never pass across Earth. The geometry also plays a role in how timing quality develops. A clean, sharp pulse with a stable shape allows very precise measurements of arrival times, while a broad complex pulse introduces more uncertainty. For a cluster, pulsar signals must already travel through turbulent plasma before reaching telescopes, so a favourable beam geometry becomes especially helpful. In the case of PSR J1748 2446ad, the combination of a fast spin and likely narrow pulses offers the potential for high timing precision, balanced by the challenges of eclipses and scattering along the line of sight. Over long periods, the beam geometry may evolve slightly, as the neutron star's spin axis precesses very slowly, or as the emission zone shifts in altitude. These changes would gently alter the observed profile without disrupting the underlying rhythm. From a calm perspective, the beam geometry and duty cycle turn the invisible magnetic and rotational structures into a readable pattern. Each short flash carries information about the path through the beam and the state of the magnetosphere at the emission height. Step by step, as the pulses are gathered and compared, that information becomes a quiet map of how PSR J1748 2446ad directs its energy into space, and how a single narrow cone of radiation allows this tiny star to be seen across the crowded depth of Terzan 5 and the inner Milky Way. In the timing of PSR J1748 2446ad, each radio pulse acts like a tick of a distant clock. The pulses arrive with high regularity despite the complexity of their surroundings. Pulsar timing uses those ticks to measure rotation, orbital motion, and tiny changes in the star and the medium between it and Earth. The core idea stays calm and straightforward. Observers record the arrival times of many pulses, correct them for motions of Earth, and compare them with a simple model of a perfectly steady clock. Any difference between predicted and observed times, even one far smaller than a heartbeat, carries information. For a millisecond pulsar that turns hundreds of times each second, single pulses are very brief and often faint. Observers do not rely on one pulse at a time. They fold thousands of rotations together, lining them up on the spin phase to build a sharp average profile. This process strengthens the regular pulse shape and suppresses random noise. It builds a stable template that represents one ideal rotation of the star. Analysts then slide this template across the data and measure how much it must be shifted to match the observed pattern. That offset reveals the exact arrival time of the combined pulse train. For PSR J1748 2446ad, with its rapid spin and narrow duty cycle, this method is especially powerful. It can measure arrival times with precision far better than the length of one rotation. Over weeks, months, and years, those precise times link together into a timing solution. That solution is a set of parameters that describe the spin frequency, its slow change, and the details of the binary orbit. The orbit introduces periodic advances and delays because the pulsar moves toward and away from Earth as it circles its companion. When the neutron star moves toward the observer, pulses arrive slightly early. When it moves away, they arrive slightly late. This gentle Doppler effect draws a smooth wave in the timing data. From that wave, the orbital period size and orientation can be inferred. On top of that, long-term trends reveal how the spin very gradually slows as rotational energy leaks away into radiation and winds. In an ideal case, once these effects are modelled, the remaining differences between data and model would be tiny and structureless. Real timing data, however, often contain a background of wandering variations called red noise. Red noise refers to slow correlated deviations that grow larger on longer timescales, like a random walk. In pulsars, this noise can arise from small irregularities in the rotation or changes in the magnetosphere. It can also appear through shifts in the medium that radio waves cross on their way to Earth. For a cluster pulsar such as PSR J1748 2446ad, additional contributions may come from acceleration in the cluster gravitational potential. They may also come from subtle changes in the line of sight through intracluster gas. These influences add a gentle, restless component to the timing residuals. They do not destroy the overall regularity, but they limit how finely the clock can be read. Astronomers respond by extending observations over longer spans, refining models, and characterizing the noise itself. Once this background is understood, it can be folded into the analysis so that real signals and slow wanderings are separated. Even after such corrections, there remain practical limits. The pulsar in Terzan 5 is faint and sometimes eclipsed by gas from its companion, so not every rotation can be used. Scattering and dispersion along the line of sight blur the pulses at low radio frequencies. That blur reduces timing precision. Instrumental imperfections and radio interference add further uncertainty. Despite all of this, the timing of PSR J1748 2446ad still reaches remarkable precision because the basic signal is so regular. Each new observation narrows uncertainties on the spin rate, the orbit, and the environment. Over the years, the collected data trace a calm story of a star that slows only slightly, while circling its companion in a predictable rhythm. From a wider perspective, this timing accuracy turns the pulsar into a quiet tool. It can weigh its companion and probe the gravitational field of the cluster. It can also test how well simple models of spin-down and magnetospheric torque describe an extreme millisecond pulsar. Small deviations, instead of being nuisances, become gentle hints about processes that would otherwise remain hidden. In this way, the practical limits of timing do not break the picture. They simply wrap the clock in a soft band of uncertainty. Inside that band, the steady heartbeat of PSR J1748 2446ad still stands out clearly against the slower, wandering background noise of the universe. For listeners, it is enough to know that behind each measured arrival time lies careful work, disentangling signal from noise. That effort slowly sharpens the view of this tiny distant clock. The pulses that blend into a soft, steady rhythm in a relaxing audio track are the same pulses used in the analysis. When examined in detail, they allow the inner workings of PSR J1748 to be traced with patient, soothing precision. When the pulses of PSR J1748 2446ad cross the deep gravity well of its companion, they carry a quiet imprint of relativity. In simple terms, strong gravity slows time slightly and stretches the path that light and radio waves follow. This effect means that pulses passing behind the companion arrive a little later than they would in empty space. The additional delay known as the Shapiro delay is small in absolute terms, but measurable when many pulses are timed with care. In a close binary system, the orbit carries the neutron star and its companion through repeating configurations. At some phases, the pulses travel through regions where the gravitational potential is strongest. At others, they move along less curved paths. The timing pattern reflects these changes. When the neutron star moves to a place where the line of sight passes near the companion, each pulse must cross a slightly deeper valley in spacetime. The delay grows smoothly as the alignment approaches the tightest passage and then falls away again as the geometry relaxes. Over one full orbit, the timing curve shows a gentle characteristic shape. This pattern can be fitted with models based on general relativity, and from that fit astronomers extract information about the mass of the companion and the inclination of the orbit. A heavier companion produces a deeper valley and a larger Shapiro delay. A more edge-on orbit strengthens the effect because pulses pass closer to the companion's limb from the observer's point of view. For PSR J1748 2446ad, The rapid spin and binary nature create an especially sensitive system where even small relativistic influences become visible over time. Alongside the Shapiro delay, there are other slow relativistic touches. The binary does not follow a perfect Newtonian ellipse. The point of closest approach in the orbit, called periastron, can drift forward over time as spacetime curvature alters the motion. This periastron advance is usually small in low-mass systems, but with precise timing it can still be traced. It adds another slowly changing phase to the arrival times, one that accumulates over many orbits, like a gentle twist in the orbital pattern. The pulsar itself also lives in strong gravity. Clocks attached to its surface tick slightly more slowly than clocks far from any mass. The pulses carry that gravitational redshift as part of their basic period. Combined with special relativistic time dilation from the star's fast motion, these effects create a constant offset between the star's internal time and the time kept by distant observers. Pulsar timing absorbs this offset into the measured spin frequency, so it does not break the regularity of the signal. Still, its presence reminds that each tick of the neutron star is set within a curved space-time landscape. Over the long term, all these relativistic pieces assemble into a coherent timing model. The model contains classical parameters such as orbital period and eccentricity, along with post-Keplerian terms that capture Shapiro delay, periastron advance, and related corrections. For a simple, nearly circular orbit, some of these contributions may be small, but even small corrections can matter when pulses are timed to microsecond precision. In a soothing view, the binary of PSR J1748 2446ad and its companion feels like a delicate clockwork placed within a flexible medium. Gravity slightly warps that medium wherever mass gathers. The pulses travel along the easiest available routes through this curved background. Each route has its own travel time, just as paths through gently rolling hills take different times to walk. Timing analysis is the art of mapping those hills from far away by watching how long each journey takes. The practical consequence is that pulsars in binaries become natural laboratories for general relativity. They test whether spacetime behaves as expected when compact objects move in tight orbits. In some systems, timing has confirmed relativistic predictions to high precision. For a record spinner like PSR J1748 2446ad, the focus lies more on what its extreme spin and binary geometry allow rather than on breaking new ground in gravity tests. Yet the same mathematics applies. The narrow pulses provide clear markers. The cluster environment adds a calm, slowly changing background gravitational field from the combined mass of Terzan 5. That field gently accelerates the whole binary, adding another smooth term to the timing data. The combination of stellar gravity cluster potential and relativistic curvature forms a layered landscape for the pulses to cross. Even with so many influences, the essential signal remains tranquil and regular. The neutron star turns the orbit carries it around its companion, and space-time adds subtle delays and advances that can be predicted and measured. From this perspective, relativity does not disturb the serenity of the system. Instead, it adds fine texture to the ticking of this distant clock, allowing observers to weigh invisible stars and trace the gentle bending of time and space inside the crowded heart of Terzan 5. As the radio pulses from PSR J1748 2446ad leave the tight embrace of its magnetosphere, they begin a long journey through magnetized gas that gently reshapes their signal. On this path, two quiet processes stand out. One is dispersion, which stretches pulses in time. The other is polarization rotation, which slowly turns the direction of the wave's electric field. Together they turn the pulsar into a probe of the material between the neutron star and Earth. Dispersion arises whenever radio waves move through a thin sea of free electrons. A free electron is simply a charged particle no longer bound to any atom. In such a medium, low-frequency waves travel slightly more slowly than high-frequency waves. Each pulse which leaves the pulsar as a brief sharp event becomes spread out because its low-frequency components lag behind its higher ones. The amount of this stretch depends on the integrated density of electrons along the path. Astronomers summarize that quantity in a single number called the dispersion measure, or dm. In simple terms, dm counts how many electrons lie in a column between the source and the observer. A larger dm means more delay at low frequencies and a more strongly swept pulse. For PSR J1748 2446ad, sitting deep inside Terzan 5 and behind gas and dust near the galactic center, the dispersion is significant. Low-frequency pulses arrive noticeably later than high-frequency ones. In practice, observers correct for this effect by shifting different frequency channels back into alignment. After this correction, pulses regain their sharp shape and timing precision improves. The very correction that removes the smearing also reveals the total amount of free electrons along the line of sight. In this way, PSR J1748 2446ad becomes both a clock and a measurement tool tracing the integrated gas content in and around the cluster and through the inner Milky Way. Polarization adds another layer of information. Radio waves from pulsars are often strongly polarized. Polarization describes the direction in which the electric field oscillates as the wave travels forward. In a linearly polarized wave, that direction stays fixed in a plane. In a circularly polarized wave, it rotates steadily. The emission process in the magnetosphere naturally favors certain directions of polarization tied to the magnetic field lines. As the wave leaves the pulsar, it carries a pattern of polarization angles across the pulse, like a fine texture laid over the brightness profile. When this polarized wave moves through a magnetized plasma, the medium behaves like a slow twisting lens. The combination of free electrons and a magnetic field along the path causes the plane of linear polarization to rotate with frequency. Lower frequencies are rotated more than higher ones. This phenomenon is called Faraday rotation. Its cumulative effect along the line of sight is expressed as the rotation measure, or Rm. In plain language, Rm reflects both how many electrons lie along the path and how strong and ordered the magnetic field is in the direction of travel. By measuring how the polarization angle changes with wavelength squared, astronomers infer Rm, and with dm already known, separate the typical field strength from the electron density. For a pulsar in Terzan 5, this measurement offers a gentle way to sample the tangled magnetic fields in the cluster and its surroundings. As the pulses from PSR J1748 2446ad cross the cluster core intracluster gas may add its own contribution to dm and Rm. Beyond the cluster, the inner regions of the galaxy contribute additional electrons and magnetic fields. The combined effect is a smooth frequency-dependent twist of the polarization direction. Observers can watch the polarization angle swing as they tune across the pulse in frequency. Once this swing is modelled and removed, the original pattern of polarization tied to the magnetosphere emerges more clearly. That pattern carries clues about emission heights and field geometry near the star. From an audio-focused perspective, all of this remains hidden beneath a simple, steady sound. Yet in the underlying data, each pulse is a finely structured object, with arrival time, frequency sweep and polarization angle, all changing in ways that respond to the path taken. The magnetized gas does not scramble the signal. It simply imprints a gentle code on it. Decoding that pattern turns PSR J1748 2446ad into a messenger of its environment. The same pulses used earlier to time the orbit and trace relativistic effects also map electron densities and magnetic fields along the line of sight. Viewed broadly, dispersion and polarization turn the space between the pulsar and Earth into part of the instrument. Instead of being a blank void, it becomes a transparent, slightly refractive medium that shapes the waves in predictable ways. For a record spinner embedded in a dense cluster near the galactic center, this is especially useful. It allows the cluster's hidden gas and fields to be explored without disturbing their quiet state. Step by step, the journey of each pulse can be felt as it leaves. The magnetosphere crosses the cluster and threads the inner Milky Way. By the time it reaches a radio dish, it carries not only the beat of PSR J1748 2446ad, but also a soft record of every magnetized pathway it has crossed. Beyond the radio band, PSR J1748 2446ad sits inside a high-energy landscape where X-rays and gamma rays offer quieter, complementary views. The central idea is that not all of the neutron star's activity appears as radio pulses. Some of it emerges as hotspots, faint glows and occasional flashes at higher energies. These windows reveal how the star exchanges energy with its surroundings, how its surface cools, and how its magnetic fields guide particles at greater heights. During the earlier spin-up stage, when accretion from the companion is strong, the system shines as a bright X-ray source. Gas from the accretion disk falls onto small areas near the magnetic poles and releases gravitational energy as heat. That heat radiates in X-rays, turning the neutron star into a compact beacon in high-energy light. At that time, the radio pulsar mechanism is usually hidden, drowned out by the thick inflow of plasma and radiation. As accretion weakens and the disk thins, the scene gradually changes. The magnetic field pushes inflowing matter back more effectively, and eventually the radio beams turn on. Even after this transition, a memory of past accretion lingers in high-energy signatures. Residual hotspots on the surface continue to emit soft X-rays. These spots may coincide with the polar caps that now serve as the footpoints of open magnetic field lines. In a calm view, the star cools unevenly with slightly warmer patches that rotate in and out of sight each spin. Sensitive X-ray observations can sometimes detect this rotation as a faint flicker tied to the spin frequency. Matching those flickers with radio timing links surface patterns to magnetospheric structures. In the case of PSR J1748 2446ad, its location in a crowded, dusty cluster makes X-ray studies challenging but not impossible. The cluster core hosts many compact objects, each contributing to the total emission. Careful analysis separates individual sources and searches for periodic signals at the known spin rate. When such signals are found or constrained, they refine ideas about how hot the polar caps are and how much residual accretion might still occur. Above the surface in the magnetosphere and near the light cylinder, particles accelerated along magnetic field lines can also emit high-energy photons. Curvature radiation, and inverse Compton scattering, where fast particles transfer energy to softer photons, can push a fraction of the emission into the X-ray or even gamma-ray range. In some millisecond pulsars, this leads to a steady high-energy component that traces regions far above the surface. For PSR J1748 2446ad, any detected high-energy counterpart would offer clues about where most of the acceleration takes place in such an extreme spinner. Even when gamma rays are not clearly seen, upper limits still matter. They constrain how much energy the magnetosphere can channel into the highest energy photons without violating observations. That in turn shapes models of the electric fields near the polar caps and along the open field lines. If the star spun only slightly faster, some models suggest that instabilities or excessive particle losses could set in, disrupting the delicate balance described earlier. The current high-energy output, or its absence, hints at how close PSR J1748 2446ad sits to these theoretical thresholds. Around the binary interactions between the pulsar wind and the outflow from the companion may create additional high-energy features. Where the relativistic wind from the neutron star meets the slower, denser gas from the companion, a shock can form. In that shock, particles may be accelerated again, emitting non-thermal X-rays that vary with orbital phase. In a few pulsars with evaporating companions, such intrabinary shocks produce distinct orbit-locked X-ray modulations. If similar patterns exist in this system, they softly record the ongoing exchange of energy between the neutron star and its partner. From a broader perspective, Terzan 5 glows in X-rays and gamma rays due to its entire population of compact objects. Millisecond pulsars, quiescent low mass, X-ray binaries, and cataclysmic variables all contribute. PSR J1748 2446ad is one member of this ensemble, adding its own small but significant share. The cluster thus becomes a high-energy mosaic, with each compact source acting as a pixel. Observations across different bands slowly fill in that mosaic, tying radio pulses to their hotter or more energetic counterparts. For a relaxing mental picture, the cluster can be imagined as a dim star cloud, sprinkled with tiny invisible embers. Most embers glow primarily in radio, some in soft X-rays, and a rare few in harder light. PSR J1748 2446ad belongs to this hidden family of embers, its extreme spin shaping both its magnetosphere and any high-energy emission that escapes. Even if its X-ray and gamma-ray signatures are faint, the limits themselves trace the flow of energy, from rotation into heat particles and radiation. Step by step, combining radio timing with high-energy observations builds a calmer, more complete view. The neutron star is no longer just a clock, but a balanced engine that divides its lost rotational energy among several quiet channels. Surface hotspots cool magnetospheric particles, radiate shocks, sometimes flare, and the surrounding cluster absorbs and redistributes the output. In this layered picture, PSR J1748 2446ad stands as a modest but telling contributor to the high-energy life of Terzan 5. Its record-breaking spin felt not only in the sharpness of its pulses, but also in the gentle extended glow that high-energy instruments trace around the crowded heart of the cluster. As the signal from PSR J1748 46ad leaves Terzan 5, it begins a long, gentle crossing through interstellar gas that gradually softens and reshapes every pulse. Dispersion stretches the pulses in time, but scattering and scintillation give them their finest grain. Scattering happens when radio waves meet small-scale irregularities in electron density, tiny clumps and ripples in the gas that act like a very weak, uneven lens. Instead of following one clean path, the wavefront is broken into many slightly different routes, each with its own small delay. When these scattered pieces arrive together at a telescope, they blend into a broadened pulse with a faint trailing tail. For a distant pulsar in a dense direction like the galactic bulge, that tail can be long enough to blur the sharp edges of the intrinsic profile. The result is a softened version of the original signal, with fine details smoothed away by the turbulent gas. At higher frequencies, the effect fades and the pulses regain some of their crispness. In this way, each frequency band offers a slightly different view of the same underlying clock. For PSR J1748 2446ad, whose pulses are already compressed into tiny slices of time, scattering can hide the full sharpness of the beam at some frequencies. Timing experiments therefore favor bands where the balance between signal strength and scattering broadening is gentle and manageable. Overlying this broadening is the quieter phenomenon of scintillation. Scintillation is the twinkling of pulsar signals, an effect similar in spirit to the way starlight flickers when passing through Earth's atmosphere. Here, however, the interfering structures lie in the interstellar medium far from any planet. As radio waves from the pulsar cross a patchy plasma, different paths interfere constructively and destructively at the telescope. At some frequencies and times, the interference strengthens the signal, at others it weakens it. The result is a pattern of bright and dim patches in time and frequency called a scintillation pattern. In a dynamic spectrum, this pattern appears as drifting streaks and islands of enhanced brightness. For a millisecond pulsar with such a short period, these variations do not disturb the basic rhythm, but they make some observations naturally clearer than others. By studying the scale and motion of these patterns, astronomers infer the typical size and speed of the scattering regions between Earth and the pulsar. In a sense, the pulsar acts as a backlight, illuminating the moving texture of the interstellar medium. For PSR J1748 2446ad, the line of sight passes through the gas of Terzan 5, then through the thicker regions of the inner Milky Way. Each layer imprints its own contribution to scattering and scintillation. Near the cluster, intracluster gas may add small angle deflections that broaden the pulse slightly and introduce slow changes in brightness as Terzan 5 drifts through the galactic field. Farther out, larger-scale turbulence in spiral arms adds additional overlapping screens. Over months and years, the overall pattern changes as relative motions shift the alignment between pulsar scattering regions and Earth. From a calm perspective, this process never disrupts the basic reliability of the pulsar. Instead, it gently modulates the clarity with which the pulses arrive. Some observing sessions enjoy bright, well-focused signals. Others must work with softer, more scattered pulses. The underlying star continues spinning at the same remarkable rate, indifferent to the small swirls of plasma along the way. For relaxation, it helps to picture the pulses as beads of sound moving through a shallow, slowly rippling pool. The beads keep their spacing, but ripples occasionally blur their reflections and change their apparent brightness. In analysis, those ripples carry information, not just disturbance. They reveal where the pool is deeper, where currents flow, and how the surface shifts with time. Likewise, scattering and scintillation from PSR J1748 2446ad trace the hidden structure of gas along a complex sightline into the galactic bulge. Step by step, combining these effects with dispersion and polarization measurements, astronomers build a layered picture of the medium between the pulsar and Earth. The same signal that soothes as a steady distant ticking also serves quietly and continuously as a probe of the invisible weather in interstellar space from the crowded heart of Terzan 5 out to the quieter regions surrounding the solar system. In this picture, the interstellar medium no longer feels like a simple void, but a gentle, structured haze. Each pulse must weave through that haze, following slightly different paths that still converge at the dish. The changes they suffer along the way are small enough to leave the fundamental message intact. They simply round off sharp corners and breathe a slow, shifting pattern into the arriving train of pulses. For PSR J1748 2446ad, this means its record spin is always heard through the soft filter of its environment, rather than in perfect isolation. In the next step of the journey, attention can return to the pulsar itself, and to how all these layered effects together set the practical limits on what can be known about this fastest of stellar clocks. In the end, the story of PSR J1748 2446ad settles at a quiet boundary between what is known and what remains hidden. Everything described so far, from its dense interior to its magnetosphere and beam, is inferred from a small stream of radio pulses that reach Earth through the crowded heart of Terzan 5. Those pulses carry remarkable detail, yet they represent only one narrow slice of the star's full behavior. The beam points in a limited direction. The line of sight crosses only one path through the cluster, and telescopes listen in finite bands with limited sensitivity. Together, these simple facts create selection effects that gently shape what can be seen and what must be left to careful imagination. For every neutron star whose beam sweeps across Earth, many others likely remain unseen because their beams never intersect this planet. Some may spin more slowly, some may spin more quickly, and some may no longer shine as radio pulsars at all. If a star similar to PSR J1748 2446ad exists with a beam that misses Earth by only a small angle, it would stay absent from catalogues its record-breaking spin unmeasured. The fastest known pulsar is therefore not necessarily the absolute fastest spinner in the galaxy. It is the fastest that happens to shine in the right direction and through a path that current instruments can follow. In Terzan 5 alone, many neutron stars almost certainly wait below the detection threshold. Their beams may be narrow, their pulses heavily scattered, or their signals eclipsed for most of the orbit by companion winds. Some systems may be buried so deep in intracluster gas that low-frequency emission is washed out beyond recognition. Others may emit mainly in bands that have not yet been explored in detail. The cluster in this view is like a field where only a few tallest stalks are visible above mist. PSR J1748 2446ad stands among those visible few because of a fortunate combination of beam geometry, orbital configuration, and observing frequency. On the instrumental side, every survey has its own quiet boundaries. Telescopes operate in selected frequency ranges and for finite observing times. Detection pipelines search for periodic signals within particular windows of spin frequency, orbital period, and dispersion measure. Very fast pulsars in tight binaries can be especially hard to find because orbital motion smears their signals into broader tracks in the data. Specialized search techniques recover many of them, but no survey can be perfectly complete. There is always a region of parameter space where signals become too faint, too scattered, or too complex to rise above noise. PSR J1748 2446ad sits near that edge. Its pulses are faint, its orbit brings long eclipses, and its position in a crowded cluster complicates analysis. Yet with patient work it emerges from the noise as a steady, almost metronomic tick. The fact that this system can be timed at all shows how far techniques have progressed. It also underlines how much may still lie just beyond reach. From a calm distance, the record spin appears less as a sharp boundary and more as a current marker on a moving frontier. Future instruments with greater sensitivity, wider bandwidth, and more powerful processing may shift that frontier outward. They may reveal pulsars that spin even faster or reside in still more challenging environments. They may also uncover many slower, softer sources, filling in the population around PSR J1748 2446ad and clarifying how unusual it truly is. Whatever new discoveries come, the essential lesson remains gentle and stable. Knowledge of neutron stars grows through a combination of direct measurement and thoughtful acknowledgement of limits. Observers accept that some beams never point toward Earth, that some signals are scattered away, and that some systems resemble this record holder, yet stay quiet in the data. Within those limits, each well-studied pulsar becomes a trustworthy anchor. PSR J1748 2446ad serves as one such anchor, showing that matter can remain intact under extraordinary spin, and that cluster environments can lift neutron stars to speeds near theoretical breakup. At the observational limit, the pulses that reach Earth mark the edge of what can currently be read from this small, dense star. Beyond that edge there is space for measured speculation, and for quiet appreciation. The star continues to turn inside Terzan 5, whether it is watched or not, its beam, sweeping through space, its magnetosphere humming and its interior holding firm. For now, the data outline a complete enough picture to follow the story from the cluster halo down to the light cylinder. The remaining details fade smoothly into the unknown, as if the view simply grows softer at the edges rather than ending abruptly. In that softness, PSR J1748 2446ad rests as the fastest known cosmic clock turning silently beneath the stars of Terzan 5 and gently marking a limit between the part of the universe already mapped and the part that still waits in the dark. Across the span of Terzan 5, PSR J1748 2446ad continues to turn in steady silence its 716 rotations each second, unfolding without haste or strain. The dense interior holds its structure layers of ultra-compressed matter, quietly supporting the spin. Above the surface, magnetic fields remain anchored, shaping the magnetosphere into a stable cage that rotates as a whole. Polar caps continue to launch thin streams of particles, and pair cascades renew the surrounding plasma in a gentle repeating rhythm. At the light cylinder, ordered motion yields to a soft outflow of wind carrying away a small portion of the star's rotational energy with every passing moment. The radio beams sweep through space on each turn, tracing invisible circles that only occasionally intersect a distant world. When the beam crosses Earth, a pulse arrives and blends into the calm background hum of Terzan 5 and the inner galaxy. Timing work distills those pulses into a precise record, but the star itself simply keeps turning indifferent to models and measurements. Around the neutron star, the cluster holds its shape a rounded cloud of ancient suns wrapped in dust and thin gas. Stars drift slowly within the shared gravitational well, while compact remnants glide along quieter orbits closer to the core. Gas fields and scattered particles form a soft medium through which every pulse must travel, adding a little smoothing and a hint of wonder to the signal. Through all of this, the essential rhythm of PSR J1748 2446ad remains unchanged, a tiny but enduring heartbeat set against the broad, dim glow of Terzan 5. Far beyond the cluster, the pulses fan out into the Milky Way and gradually fade into distance. What remains is the idea of a compact, resilient star spinning calmly at the edge of what dense matter can support, and doing so without drama. In that image, the crowded cluster, the magnetosphere, and the journey through interstellar space all soften into one continuous peaceful scene, with the fastest known pulsar turning steadily at its center.